Hello. Can you hear me? Hello.
Hello?
Hi.
Okay, I can hear you. So we're doing rocket science today?
Yeah.
Okay, have you had a chance to read it?
Oh, sorry.
Okay, I think this rocket science is a tough one. This one's a little bit more confusing than some of the ones we've done in the past. So do you want to get a chance to read it, or what do you want to do?
Yeah, I'll take a minute to read it.
Okay. Yeah, you can let me know once you're done reading up to the first question, and then we can work through the first question.
All right.
Okay, so you're on the first question now?
Yeah.
Now, this one, this is just about the angular momentum vector, right?
Yeah.
You feel you know how to do that?
Sketch.
So sketch the initial angular momentum vector. You're on that question?
Yeah.
Okay, so to do that, what do you know about the angular momentum vector? About what direction it should face?
Uh, well, it should. Uh, After the long axis, the rock has been rotated counterclockwise through a very small angle. Well, it would be counterclockwise with the long axis of the rocket, right?
What do you mean by counterclockwise? So vectors have a direction. What do you mean by counterclockwise? So there's rotation that's either clockwise or counterclockwise, but there's always some direction of the vector which could be determined using something like the right hand rule, for example.
All right. Yeah, so it would be like, well, given the diagram, with the diagram given, it would be in the positive x direction.
You're saying the angular momentum vector is perpendicular to the omega vector?
Oh,
Why would you say positive x direction?
the long.
What makes you say it would be positive x direction?
I was just thinking that I was just using the right hand rule.
So you're taking your so for right hand rule based on what? So for the right hand rule, which right hand rule do you use? Do you use the one with the two fingers and the thumb, or do you use the one where you curl your fingers in a direction and then point your thumb in a certain direction?
Curl your fingers.
Okay, so you're curling your fingers from the omega vector to the negative y direction, and you're getting that the thumb is pointing in the x direction?
Yeah.
Okay, so why would you curl your... Oh, so you're looking at the rocket moving, to the left. It looks like the rocket is moving to the left according to that diagram, and so you're taking your fingers and curling them in the direction of where the rocket is moving.
Yeah, it also said counterclockwise.
Mm-hmm. Okay. Yeah, well, counterclockwise is the rotation of the rocket around that omega axis, right?
Yeah.
So first sketch the initial angular momentum. So that's before it is rotated counterclockwise.
Well, it says after.
Okay,
Both.
sketch the initial angular momentum vector and some other stuff.
Oh, it
First thing you have to do is the
wants
initial
two
vector.
different ones.
Yeah. So the first question is, what's the initial angular momentum vector?
Well, before there's any initial, would it just be 0, or what would it be
Well,
somewhere?
why would it be 0? Because it's spinning. It says the initial angular velocity of the rocket is omega, where omega is the angular speed. So
Yeah.
the initial angular momentum is omega. If omega is not 0, then the angular momentum can't be 0.
Okay. Well, for the initial, then when I use the right hand rule, again, I'll get angular momentum in the positive x direction.
Now, what exactly do you mean by right-hand rule? Because we're talking about, oops, let me get the pen. So we're talking about angular momentum. That can be written, for example, as r cross p, where you would use the right hand rule here, right? You would have your fingers. So if you have your R over here and your P over there, then you would take your fingers, point them up into the R direction, curl your fingers to the P direction, and then you'll have that the thumb is going to be pointing in the L direction. You know what I mean?
Yeah.
So where this L is going into the page. So in terms of right hand rule and angular momentum, you think of this, the cross product definition. But what exactly are you doing? Because I don't see any linear momentum vector in that image, and I don't see any R vector. I don't even know, like, what do you mean by right hand rule?
Well, I think I was just well, I guess I was using right hand rule for the wrong with the wrong things.
Yeah, yeah. So for angular momentum, the only right hand rule I can see based on what you've learned in this course is R cross P, and there's no R or P here. There is omega though. So do you know how to write angular momentum in terms of omega?
Well, in terms of omega, so linear momentum is mass times velocity, so angular would be inertia times omega.
Moment of inertia.
Yeah.
Okay, yeah, that's good. So I omega. Now the left side is a vector. What about the right side? Is the right side a vector?
Well, I a linear angular velocity is a vector, right?
It is. So the left side is a vector. What about the right side? Oh, you're saying angular velocity, right? Yeah. So angular velocity is a vector. Now, angular velocity is given to you in the first diagram, right?
Yeah.
So then what direction is the angular momentum going to point?
Well, if angular velocity is pointing in the positive z direction and inertia is scalar, then that means angular momentum has to be in the positive z direction.
Precisely. So not the positive x direction, the positive z direction.
All right.
So you've got the first part of the first question done, where it asks for sketch the initial angular momentum vector. You know how to do that now. You just draw a vector in the same direction as the angular velocity vector. And the angular momentum vector after the long axis of the rocket has rotated counterclockwise through a very small angle. So that rotation counterclockwise, I guess that's already depicted in the diagram that they gave you. Now you just have to draw where the new angular momentum vector is going to be.
All right. So that's so if there's a bit of counterclockwise rotation, uh, long axis is going counterclockwise. Well, if it's rotated at a very small angle, then I don't really know where to start.
Okay, so the rocket you're looking at the rocket diagram on page 1, right?
Yeah,
So the rocket has rotated a bit counterclockwise. They've already drawn a diagram of what that looks like.
it. Oh wait, are you trying to show me something?
No, no, you're already looking at that diagram on the page 1 of the rocket science.
Yeah,
And in that diagram, you see that it's already shown you that it's moved a bit counterclockwise,
yeah,
that dotted line, right?
yeah.
So for the dotted line, that's the new rocket position. Where is the angular momentum vector going to be pointing in that case?
Well, it would still be pointing in the same direction as angular velocity, right?
Yeah, and the angular velocity, will that change if the rocket is rotated?
Uh, I think so. Yeah, it would. Uh, yeah, it would because it's a, the inertia of the rocket spin about its long axis. Yeah, I think angular velocity would change with the angle.
Yeah, okay. And so if it changes with the angle, what about the new angular momentum vector?
It would change with it.
Yeah, so now you know what the how to answer the second part of this question. So the first part was just the initial angular momentum. You know that's going straight up in the positive z direction. For the new angular momentum, it's going to be aligned according to how the rocket has rotated, right?
Yeah.
Okay.
So it would also be it would be like in the positive z direction, but on a bit of an angle.
Not exactly in the positive z direction. It would actually be a bit rotated from there.
Yeah, I said on an angle, rotated.
Yeah, 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 yeah. So an angle away from the positive z direction.
All right.
Okay, so you've got both vectors should have their base points at the center of mass point. Okay, so in your sketch, you just have to make sure you draw the arrows that way coming from the center of mass, just like the angular velocity was in the example they gave you. Now assume for the moment that the magnitudes of the initial and final angular momentum vectors are the same and only the directions are different. So that just means you're making the lengths of the vectors the same, the initial and the final.
Is this? All right.
Okay, now the next question it asks, the next question it says, what is the direction of delta L in the limit that the rotation angle approaches 0? So do you know how to do that?
I just gotta write a few more things down.
Yeah.
All right. What's the direction of L? The limit that the rotation angle approaches 0. direction. Well, if the angle approaches, okay, so no, well, if the rotation angle approaches zero, then L would just be in the positive z direction, right?
So delta L, how do you justify that? So do you know what direction delta L is going to be facing in?
So it would be the change in L. So yeah,
So we have L final minus L initial. So we have L final minus L initial. So that's L final, that's negative L initial. So we're going to have something like that.
right.
Okay. And L final and L, so L initial is completely vertical. And so L final will be an angle theta away from that, right? So this angle, that would be theta. Actually, I think I've not drawn this very well at all. So I'm just going to make it bigger. So we have a vertical line like that. And we have L final is going to be an angle theta away from it. And then L initial would have to be, well, this is negative L initial. This is negative L initial.
Yeah, if you use the Z rule,
Yeah. Yeah, you can use
the top angle would be theta.
Precisely. Yeah, that's true. So here's your delta L vector. And now in the limit where theta goes to zero, what's going to happen here?
So if theta goes to zero, then that means L would go in the negative y direction from what I'm seeing.
Okay, so if theta goes to zero, we will have basically, we have this vertical line again. And we have basically that we have this vector LF, and I should have put the theta like that. So this is LF with an angle of basically theta being zero. So then we have also that, this is going to look ugly. So basically, I'm not going to draw the negative Li vector, but you know that the negative Li vector is going to basically be just vertical down like this. So my, hold on, is it that way? So LF minus Li yeah, so L delta L should be pointing this way then, right?
Yeah.
LF minus Li. Yeah, because basically, as this angle gets smaller and smaller, this vector is going to turn. This vector is going to go more and more horizontal. until it's basically a tangent that's exactly horizontal. Okay, so that's the first part of question 2. What is the direction of the torque that must be applied to the spinning rocket to produce this increment of rotation of its long axis? So if we want the rotation to move that way, if we want its long axis to move by this angle theta, what direction does the torque have to be applied?
Okay, so the change in momentum in the negative y direction. We have the fact that the change in yeah. Yeah, that makes sense. So as using this as time approaches 0, then L would approach infinity, right? Or
No, that's not how derivatives work.
oh,
Because as delta t goes to 0, delta L, so why would L go to infinity as time goes to 0?
yeah, you're right. So we know that delta L is equal to torque times time. That's yeah.
L,
The torque is the constant during a small interval t. This equation says that the corresponding small change in angular momentum is delta L equal to tau delta t.
where does it? Oh, okay, yeah. So if the torque is approximately constant during a small time interval delta t, then the equation says that the corresponding small change in angular momentum during that time is okay. Yeah, I would say this is an approximate relation because yeah, that's I would say okay, well, yeah, if it's constant, then you basically have like a linear y equals mx plus b kind of thing, where your slope is just calculated from the rise over the run. So yeah, so basically torque and delta L have some relation to each other. They're in the same direction?
Well, I mean, it makes sense because torque is what, yeah, because this, yeah, because torque directly relates to momentum.
Yeah. Yeah, so yeah, so the delta L, so delta L and tau should basically be in the same direction, right?
Yeah,
Okay, and does that make sense to you? So we want to push this rocket. We want to rotate this rocket this way, and that means that our torque has to go tangent to that circle of
yeah,
rotation.
yeah,
Okay. Also, torque also equals R cross F, right?
yeah,
So your pivot point, where is it pivoting? It's pivoting around this point over here. And if you drew the R vector from the pivot point to the force that's causing the torque, you would have a vector going up like this. And then your force, I guess your force would be going away from, no, into the screen. You would get R cross F. Yeah, so if the force was going into the screen, then your R cross F would have your thumb pointing in the negative Y direction, which is basically what we drew for the torque vector.
all right.
Okay, so now what is the minimum? So question, the next part, you're okay with questions 1 and 2?
Yeah,
Okay, so let's go on to the next part. So this was just part 1. You've got these on GitHub, right? You've got the slides?
yeah,
Okay. Okay, so number 1, knowing the direction of the torque, discuss the following related questions. What is the minimum number of maneuvering thrusters needed? Do you think you have any idea what the answer to that is?
what's a minute? Well, sure. I want the center of mass to move. I guess it would be 2. Would it be 2?
Why would it be different from 2?
Wait. Well, well, 1 might work.
Well, if you have 1, then how is the net force going to be 0? It says the net force applied to the rocket has to be 0.
Oh,
So you want
okay.
a torque, but without any net force.
All right, so it would be 2.
Okay, so
Because,
you need at least 2 to cancel out the first one, right?
yeah, or else because like if you only have 1 rocket, you can't cancel out only one with only 1 force.
Yeah. Now there's more complicated scenarios in which you would need a minimum of 4 thrusters for a rocket. So there's scenarios where you'd need a minimum of 4 thrusters. On the Space Stack Exchange, space.stackexchange.com, there was someone that asked about that, and there was a detailed answer about why you would need 4. But I don't know if this is meant to get to that level of complication. I think if you have 2, then you need the second one to cancel out the first one, right?
Yeah.
Do you end up getting the answers to these at the end?
No.
They don't, and they don't evaluate you on it.
No.
It's just group work. Okay. So yeah, for the group work, I think it would be sufficient to say that all forces need to be canceled out. And so therefore there has to be an even number of forces. The smallest even number happens to be 2. What else are they asking here? Exactly where on the side of the rocket should they be attached? Can you think of what the answer to that must be?
So I'm still writing down the answer. Just a second.
Mm-hmm.
Exactly where on the side of the rocket should they be attached? R cross F. The base point for the vector R. Well, exactly where on the side of the rocket should be attached. Okay, which direction? Well, how is it equal to R cross F?
Yeah.
So, where's the, well, the base point, would it be center of mass?
Yeah. That's well, it would be the pivot point. So how is it rotating?
It's rotating. It's rotating through the long angle of the rocket.
The long axis of the.
Yeah.
Okay. Yeah, we want to rotate it counterclockwise in the YZ plane. So it's in the YZ plane and it's rotating. So if we drew the YZ plane, okay, so this is Y and Z, then it's rotating like that.
Yeah.
So we have the rocket, like at some point in time, like that, and it's rotating like this. So the axis of rotation would then be, where would the axis of rotation be?
The axis of rotation would be counterclockwise. Oh, the center of mass.
Center of mass, but it would be basically in the x direction, right?
Yeah.
So if it's going counterclockwise, then I guess it would be in the positive x direction. So we would have some, in 3 dimensions, you'd have this positive x and negative x.
Yeah.
So it would be rotating around that x axis. And yeah, it would rotate around the center of mass typically. So the r vector is going to go from that central point to where the force is. And then the question is where to put the forces. Where should we put these thrusters? Exactly where on the side of the rocket should they be attached?
Well, if it moves that like that, I guess seeing exactly where. Well, there's, I guess, to counteract. Wait, and we need these thrusters to cause this rotational motion.
Yeah, the thrusters are basically going to cause the rotation.
Okay, so we need the thrusters to make this counterclockwise motion.
Yeah.
Okay, so in that case, the first one would be sticking out the top right of the rocket.
Top right, meaning here?
Maybe not the center though.
Why not the center?
Because we're trying to make a actually I guess that would work.
What? So you were saying to put it here in the top right?
Yeah, but then but yeah, I think that would that would
What was your reasoning for putting it in the top right?
because it would be farthest away from the center of mass, so it would cause the largest torque,
Oh, I see.
but maybe that's not the best choice.
Yeah. Um, yeah, you're thinking quite far ahead, perhaps.
Right.
I mean, you're choosing where you're trying to minimize the amount of force that you need to do when it's just saying, and it's just saying which where should they be attached and in what directions should they be pointing. So it's not really too worried about how much force. Yeah, maybe you could try to optimize how much force how much fuel you need for those thrusters, but um, yeah, let's just so in the actual question, if you scroll down to the next page, they actually draw it for you.
Yeah, let me see. You mean page 3 out of 5?
Yeah, at the bottom of page 3, they actually draw the thruster. So they've kind of given you the answer. So yeah, I mean, I guess they just wanted the thrusters to be here, I guess. So there's one of them there. Where's the other one?
I guess on the other side. Yeah, like that.
And now which direction are they pointing in? So these thrusters are basically emitting gas, just like a jet, right? The jet has it works very much in accordance with Newton's third law.
Yeah.
It
Okay.
moves forward as it expels gas backwards.
Yeah.
So by emitting a force, by pushing gas in one direction, the object moves in the opposite direction.
Okay, so well, okay, so for the thruster on the right,
Yeah.
force would be applied towards the top of the rocket parallel to its long axis. Not axis. Yeah, like that. So it would be emitting, yeah, it would be emitting the gases on that side.
Yeah. Okay. So there's a force of F going that way, and there's an equal and opposite force F going in that direction.
Yes.
Okay. Now, what about for the other one?
The gases would be emitting the other way,
Like
and the
that.
force would be going downwards like that.
Okay. So let's now just draw the R vector from the pivot point to the force. So that's the R vector to the force. And then where is the force going in order to make tau equal to R cross F? Sorry, the torque vector should be at the center of mass. So I could.
So R cross F would be okay, so that R you just drew in red, or is that in the rocket exactly?
Okay, so that's going from, yeah, let's erase that too, because that's going from the pivot point to the force.
Right.
I'm in trouble erasing this. Okay, just erase it manually. Oh, it's gone now. Okay. So, all right. Okay, so yeah, so the motion is like that. The force, so if the torque is going tangential, like parallel to the tangent of the curve, that's the torque. And how about the force vector? Where's the force coming from? So there would be a force. So there's some distance away. So if the force, yeah, if the force is being applied over here, so that's the green arrow in the diagram to the left, then your R vector will go from the pivot point to the force, and then R cross F. So R cross F. So if R, so R is in the XY, R is in the YZ plane and F is in the YZ plane, then the torque would have to go out of the page in the X direction.
Right. Yeah. What's the F? R. Okay, so R cross F. Sorry, I'm just a bit confused.
About what?
But but I, just give me a second. I need to write down a few more things. This. What? Okay. So, so you're still trying to talk about the second question?
Um, well, I'm okay if you're okay with the second question.
Yeah, I'm okay with the second question.
So, third question: as the rocket spins, at what instance of time should the thrusters be blasted? Why not have the thrusters blast continuously?
What instance of time?
So, when should the blasters emit the force?
And the rocket is spinning counterclockwise, right?
Yeah. Counterclockwise in the YZ axis.
Okay. Well, I'm just a bit confused on. Okay, so it says at what instance should the thrusters be blasted? I'm just confused on what the goal is. Is it to make it spin more?
More than what? I mean, the goal in the end is for the rocket to rotate 180 degrees so that it is facing completely the opposite direction while still spinning. So it's spinning around the z-axis the whole time.
All right.
And we want to switch the orientation of the rocket so that it's still spinning around the z-axis, but now it's facing the opposite direction in the YZ plane.
Ah, right. It's constantly spinning in the, you said direction?
Around the z-axis.
Okay. Okay, so if Well, I guess it would be. And when the rocket moves, would it still be spinning around its long axis or just the actual Z axis?
When the rocket moves. So when the rocket is at this angle, it will still be moving around its long axis.
All right. Well, maybe I would say something like the thruster should be placid when you see the diagram we made, only when the thrusters are aligned that way. Because if the two thrusters were facing, or if the first thruster was in the positive x direction, the second was in the negative x direction, then it would turn in the positive or negative x direction, not the it won't turn in the y or z direction. It's a bit hard to explain.
Yeah, but the question here is at what time should the thrusters be blasted?
Oh yeah, we have tau times time equals L. The torque is approximately constant during a small time interval.
It's 9 o'clock.
I'm just looking at the section. Torque changes angular momentum. Because I think that's where I'm supposed to be looking at the moment, but I just don't really know what to do.
Okay, well, they ask you why not have the thrusters blast continuously. So do you want to have the thrusters blasting continuously, or do you want them to be blasting in pulses?
Well, I guess if it's continuous, it would waste fuel.
Why would it
That
waste fuel? Would it like? Does it have to waste fuel? What if it gets the job done faster and then you don't have to use fuel as much?
uh, well, keep thinking. Torque. Well, it wants us to get to a 180-degree rotation.
Yeah,
And I guess it doesn't want us to go any further.
yeah. You don't want to go further than 180.
Yeah, so I guess that's why it doesn't want it to be continuous, or else it would just go past 180 degrees.
And by doing it with just a pulse, would that? So what if you just let me get the diagram back. What if you just blasted it continuously for the first 5 seconds and then you stopped blasting? Then would it pass the 180-degree mark?
getting past 9. We should just finish this one question and then be
Okay.
done.
Yeah, so for 3, I'll tell you that with these thrusters, some of them do actually blast continuously, and some of them blast discretely. So this discrete pulsed thruster, it's called a pulsed inductive thruster. Thruster, also known as a PIT. And this one, it blasts in bursts, in pulses. There's several advantages of that. I can even send you some information about those. This is in contrast to an electrostatic ion thruster, which blasts continuously. Electrostatic ion thruster. So this blasts in pulses. And here, the blast is continuous.
Okay. Well,
so you can think of you learned in one of the first units this impulse equals impulse. Do you remember what impulse equals?
yeah, it's equal to the mass of an object times the distance away from center of mass squared. Oh wait. Oh, sorry.
That's moment of inertia.
Impulse. Oh, impulse. It's a momentum. Oh wait, no, it's a. I've learned impulse, but we almost never talk about it.
But it was used in one of the long answer assignments.
No, isn't it force times the display it's force delta t at, or is that?
Yeah. Well, so impulse is equal to the integral of f dt, which is equal to the rate of change of momentum by the impulse momentum theorem.
Yeah.
And then you can imagine an angular version of this, right? Like where you have angular momentum instead of linear momentum, and you have torque instead of force.
Okay.
So if force is constant, if I have some force, if I have force as a function of time, and that's constant,
Yeah,
then the
yeah.
area under the curve is the impulse, right? So
Yeah.
You're starting to learn about area under the curve in your calculus class now?
Yes. We're just starting to learn integrals. So that's good, but we're not learning enough to do it well until next term.
Yeah, but that kind of stuff is going to happen throughout your education because when you start taking electromagnetism courses next term and in 2A, you're going to be asked to do vector calculus, which isn't going to be taught until your third calculus course. So you're going to be using vector calculus in your physics courses before you learn it in your math courses, and that's just the way that the courses have been planned. Wasn't planned by me. I don't think it's the best idea to do that, but
It's makes no sense.
makes no sense. But it's also been that way for decades. Like you're not the first person to experience that. It happened to me too. I hadn't even taken the vector calculus course, and I needed to use Stokes's theorem, Gauss's theorem, all that stuff for a electromagnetism course I took in my second, in my 2A term. So, well, you know, if the force is constant, then that will have consequences on what the impulse is going to be. So you could think of it that way. My time is a little bit up right now, but these are definitely, like, if you want to understand a bit more about the advantages of pulsed indicative thrusters, where the blasts come in pulses rather than continuously, then if you look up this term, there's definitely a lot of advantages that you can see online. I can also send you some materials if you're interested in that.
All right. Yeah, I shouldn't keep you waiting any longer.
No problem. Yeah, I mean, I just stayed a bit longer because I wanted to explain this diagram with impulse and force. What would happen if the force was constant and continuous versus if it was just a burst. So, okay, so I guess I will see you tomorrow.
Yeah.
And for tomorrow, so these rocket science problems, you don't usually have to finish the whole thing, right?
No.
45 minutes is never going to be enough. These are some long, there's like 5 pages worth of stuff. It's not really possible to do in 45 minutes. So for Friday, sorry, Thursday, I can do, Thursday is in person, isn't it?
Yeah.
Okay, so Thursday we can do mastering physics.
Yeah.
Excellent. Okay, that sounds good. Okay, so have a good evening then, and I'll see you tomorrow.
See you.
See you.